Hey, it's Workbench with Workbench Quagmire, back with day 89 of our free code camp Python certification in 100-ish days. Today we're going to do this lab called Implement the Depth First Search Algorithm. So let's redo it. Implement the depth first, that's hard to say, depth first search algorithm. In this lab, you will implement a graph traversal algorithm called depth first search. Whereas the breadth first search searches incremental edge links away from the source node, depth first search first goes down a path of edges as far as it can. Once it reaches one end of a path, the search will backtrack to the last node with an unvisited edge path and continue searching. Unlike breadth first search, every time a node is visited, it doesn't visit all of its neighbors. Instead, it first visits one of its neighbors and continues down the path until there are no more nodes to be visited on that path. To implement the algorithm, you'll want to use a stack, an array where the last element added is the first to be removed, and following the LIFO principle. A stack is helpful in depth first search algorithms because as you add neighbors to the stack, you want to visit the most recent added neighbors first and remove them from the stack. A simple output of this algorithm is a list of nodes which are reachable from a given node. Therefore, you'll also want to keep track of the nodes you visit. So the objective is to fulfill the user stories below and get all the tests to pass and complete the lab. You should have a function named DFS. The function should take two arguments, an undirected adjacency matrix, and a node label, which is the numeric value of the node between 0 and n-1, where n is the total number of nodes in the graph. And the DFS function should implement the depth first search algorithm and output a list of all nodes reachable from the node passed to it. So we have a visited list that we're going to return. And then, okay. In here as our test. So we have to have our stack, and that is just going to contain our start node at the beginning. Then we have our visited, and while loop. So while we have anything in the stack, the current node equals the stack dot pop. So this takes the last item off of the list, in this case our stack. If current node not in visited, so we can check and see if it's there, we're going to visited dot append current node. We got the name visited wrong. So we are just returning So here's our matrix. We are returning this right now, our start node, because that's all the code we have so far. We need to evaluate our matrix. And we need to get the neighbors. So enumerate. So we get all the neighbors for the current node. And if is connected. There's one. And neighbor not in visited. Then we stack dot append the neighbor. Oh, holy smokes. That was fast. So basically, we just take the matrix, we create our stack starting with the node, the start node. We go to the current node equals the stack.pop, which makes the start node the current node. And the current node is not visited, which it's not, so then we append it. And then for neighbor is connected, we enumerate the matrix. So go in here and print the matrix, and then print the so you can see there as it iterates through the current node. There are the neighbors. I think that's helpful to see. Anyway, that was a fast one. Do your research on how to implement the algorithm. I actually Googled about it and it gave me the JavaScript one, which is basically the same if you know JavaScript. It's not hard to transform that into Python. So thanks for watching the video. Don't forget to comment, like, and subscribe, and I'll see you next time.